Hi students, how are you? As I promised, I'm just recording a short video. Well, I'm not so sure if it's going to be short, but at least we're going to practice a little bit of everything related with integrals. So basically, the idea is to start with the most basic definition about the two things that we can calculate using integrals, double integrals to be precise. The first thing that we have to keep in mind is that we can calculate areas and also we can calculate volumes. Which is the main difference between both of them? Okay, if we want to calculate areas, we don't have to have a function here. What we have there is actually a number 1. And why is this? Because remember that an integral is a sum. So basically what we're saying here is that we are adding differentials of area. So if we add a lot of pieces of area, this small piece of area here, this small piece of area here, here, and here, like to have a bunch of areas, just like this, what we are getting at the end is the total area of a certain figure, okay? So that's why we can calculate areas using double integrals. Um, Remember also that the differential of area can be a dx dy if we are working with Cartesian coordinates, or we can rewrite it as rdr d theta, where we are considering that we're working with polar coordinates. So basically the idea is to express how can we cut this area into small pieces, and if we are doing it just considering a motion in the x direction and a motion in the y direction, or are we cutting pieces of curves like the one that I'm showing you here? And in this case, this arc that we have here, it's going to be r d theta, and we're multiplying it via dr. So with that, we're getting the area of a small region like this one. So that is the main part. We can calculate areas with double integrals because we're summing small pieces of area. So at the end, we get the total area. And remember, differential of area can be expressed as these three different things that we have here. Also, we can calculate volumes. Remember that in this case, if we want to calculate a volume, we need to have here inside the integrals a function, and here the differential of area. Remember that a function is actually a z expression. That means that when we are, I don't know, trying to draw a specific figure, we have in 3D something like this. Let's suppose here we have a paraboloid, for example, and what we are doing is that we establish a certain area here in the bottom, in the floor, and with that we get a projection, a 3D projection like this one. And what we're doing is to multiply the area that we're getting here in the floor times z, which is the height of the function. And with that, we're able to calculate the volume that we have here. Basically, that is the idea, to get the volume of this figure, multiplying the area of the bottoms times the height of the function. So that's why we can say that we are calculating volume multiplying z times dx dy. Or if we are working with polar coordinates, we can rewrite this as r dr d theta. But that is the two things that we can calculate using double integrals. We can calculate areas and we can calculate volumes, okay? Basically, that is the idea. So let me erase this screen and let's move on with the exercises once we have this analysis from here. So, let me change the slide. Okay, the second thing that we have to remember is how can we establish the area that we have in the bottom? Okay, so basically in this case, I'm providing you here a figure where we have two equations. We are trying to say that we have a portion of region where it's delimited by x squared plus y squared equal to 1 and x plus y equal to 1. So basically, they are providing us this piece of surface and also this line here. Once we identify the type of function that we have, what we need to do is to find out what is better to do in order to solve the integral. So what we need to think is if it's better to get an integration starting in the x direction or doing it in the y direction. So in this case, let me show you the first example here. What we have is an integration having as an inner integral dy. That means that we enter to the region by the line that we have here in the bottom. And we are leaving the region by going out here in the other curve that we have here, like the piece of the circle. And you will say, why these two equations are different from the original ones? Well, that is something kind of easy to answer. What we're going to consider in this piece of analysis is that if we're making an integration with respect of y, we need to solve these two formulas for y. So basically, y squared has to be 1 minus x squared. So y has to be the square root of 1 minus x squared. And same thing here. If we are trying to provide an integral starting with the with y, so from here we have to get an expression for y. So y has to be 1 minus x. And with that, we can get both of these expressions that we have here. So if we're thinking about solving something with first the y-axis or the y variable, remember, it means that we are trying to enter the region by this first line and going out, leaving it with the second one. And for the other variable, in this case x, we have to have the smallest value of x, which in this case is 0, and the highest value of x, which is 1. If you don't know which are those two values because you don't have the graph, what you need to do is to equate both of these functions in order to get a solution, okay? So in that case, what we need to do, as I mentioned, is to equate the two functions. This is y and this is also y. So this can be written as I'm showing you here. To eliminate the square root, we're going to get the second power for both of the sides that we have here. So we have it squared here and here 1 minus x squared. If we raise this to the second power, we're getting a 1 minus 2 times x plus x squared equal to 1 minus x squared. We can cancel these two things here and move all the terms to one side of the equation. So we're getting this x squared positive plus this x squared. So we're getting 2x squared minus 2x equal to 0. You can get as a common term 2 times x, and that is giving us this relation from here. Basically, if the first term is equal to 0, we can get the first value, x equal to 0. And if the second term is the one that is equal to 0, in this case, we're getting that x has to be equal to 1. Okay, so from there, we're getting the points 1 and 0 that we have here. Well, my apologies, 0 here and 1 here. Okay, that is important to keep in mind. With that, we can establish now the limits of integration. As you can see from this image, if we want to solve the integral, just in general, not for any function at a specific, let's see here, we're calculating f of x times dA. In that case, the limits of integration are going to be as they are shown here. First limit, because we're getting in by y minus x, our lowest limit, and we're going out by this piece of surface. So this has to be our upper limit, the one that we have here. And later, we have the smallest value of x and the highest value of x, 0 and 1. Because in this case, we have function times differential of area. That means that this formula is calculating the volume. Which volume? The volume that is between the floor, this differential of area, and the function, which is our z. So with that, we're calculating the volume here, okay? And if we decide to do it in the other direction, in that case, what is happening is that we're getting in by the function of the line and going out by the function of the circle. Why the equations are different? Because in this case, if we're going to integrate with respect of x, we need to establish equations in terms of x. So in this case, what we're getting from here is that x has to be 1 minus y. And from here, we are getting that x squared has to be 1 minus y squared, and x has to be the square root of 1 minus y. So basically, that is what we're doing here to calculate the limit of integration. Okay, people? So if we move on, now we can write the equations for both of them. So the limit, the lowest limit of integration is going to be 1 minus y, and here the upper one is going to be the square root of 1 minus y squared, and for x 0, and for y 0 and 1. Okay, so basically that is the way to establish in which direction are we getting the integration. What is important? Not always the reason to select one or another variable to do it is because of the region. Also, it can be by the type of equation that we have as z, as f of x, y. Why? Because there are going to be integrals that are easier to solve than the ones that we can have in the other direction, okay? So let me erase these things from here and we move on to the first example. Okay. So this is an example, so you can notice how to solve the exercise. In this case, they are asking us to calculate the volume of this function. We have here in the top the sine of x divided by x, and here we have the differential of area. So basically, this formula, what it's doing is to calculate a volume, okay? So they are not telling us, but this is actually a volume. Where R is the triangle in the xy plane bounded by the x-axis, the line y equal to x, and the line x equal to 1. I already draw this here, or I have here the representation. This line here is y equal to x, and this is x equal to 1, okay? And obviously this is the axis, and remember that if we want to write an equation for the x-axis, that has to be y equal to 0. In this case, we can do the order of integration in any direction just by the shape of the region. That means that we can do it getting in by this line and going out by this one, which means to have an integration first with respect of x, or we can do it in this direction by getting in this axis and going out in this line. So the region is not the problem. Let's see if there is a problem with the function. And here, as you can notice, we have a function that is kind of tricky. Why? Because if you're trying to think a way to solve the integral, let me write it like this. Sine of x divided by x, and we can have it like this, or we can have it in the other way. dy dx. Okay? Why? Which one is the problem? The problem here is that actually there is no way to calculate this. There is no mathematical way to do it, just by numerical methods, and that is called the error function. So there is no way that we can solve first with respect of x. This integral is impossible. If you don't believe me, go to Symbolab, let's go to Stewie, wherever you want to go, and you cannot solve this one here. Okay, so in this case, it's better to start integrating with respect of y. If that is happening, that means that we are moving in the direction of the y-axis, how the y-axis is increasing. So that means that we're getting in by this function and going out by this function. So basically, our lowest limit of integration is going to be y equal to 0. And here in the top, we're going to have the equation y equal to x. So our limits has to be 0 and x. Let me write the function just like we have it here. And with respect of x, we need the lowest value and the highest value of x, which in this case is 0 and 1. Okay? So, as you can notice, now the integral that we have here is extremely easy to solve. Why? Because all the terms that we have here are constants. So we keep the constants there and we just multiply by the variable, which in this case is y. And we need to evaluate in the limits of integration. Okay, people? If we evaluate in the limits of integration, then what we're having as a result is the constant. And instead of y, we're going to substitute the upper limit, which is an x, minus the evaluation of the lowest limit, which in this case is 0. And now, look at the beautiful thing that we have here. Because just by the way we wrote the expression, here we're getting an x, and here we have an x, so we can cancel both of them. And now we have something that is extremely easy to integrate, which is just the sign. And the integral of a sign is, okay, correct, minus cosine of x. And we need to evaluate from 0 to 1. So basically we have the cosine of minus 1, of 1, minus cosine of 0. Remember, always we evaluate the upper limit and then we subtract the lowest limit. And with that, we are done. We need just to get this into a calculator. And with that, we're getting the result. I hope you don't have questions about this, but if you have it, remember that you can send me an email at any time or a WhatsApp at any time you require, okay? So let me erase this and let's go to the next slide. Delete. Next exercise. Here we have the following exercise. In this case, we have the equation in Cartesian coordinates, okay, rectangular coordinates. And I'm just drawing the region that we have. How do I got this region here? It's important to remember that we can get it from the limits that we have here. First, they are saying that the integral is with respect of x. So that means these two here are limits of x. We have two equations, which is x equal to 0. And we have another equation, which is x equal to minus the square root of 1 minus y squared. Okay? So if you need to solve this, what do we have? X equal to 0 is the vertical line that we have here in blue. X equal to 0. And also, look, this is the expression of half of a circle. This half, which is the negative 1, is going to be 1 minus square root of 1 minus y squared, and we get the other one. So if we have the whole circle here, for example, this is 1 minus y squared, and this is minus square root of 1 minus y squared, like this. So because we're getting a negative value, that means that we're only having the left side of the equation. So with this, we can notice that basically what we have is a region which is associated to a piece of circle. And that is a clue when we're trying to solve the integrals. Why? Because if we have a piece of circle, what we can do is just to try to solve this thing here, or we can change to polar coordinates, okay? So let's do it. Let's change it into polar coordinates and let's find out. Remember, in polar coordinates, x squared plus y squared has to be equal to r squared. And what else? And what else is important? Okay. Differential of area has to be r dr d theta. So that's the things that we have to remember. Let me change colors. So basically, we can convert this double integral into a 4, a square root, and the thing that we have here inside is r squared. And here in the bottom, we have a 1 plus r squared. This dx, dy is actually differential of area, so we can change it by r dr d theta. And now we can get the limits of integration, which is the radius of the circle. The radius of the circle is running from the center of the circle, which is a 0, and reaching the circle with a radius equal to 1. So basically, the radius is running from 0 to 1. And the angle, remember that always is measured from this line here, from the x-axis. So in this case, we are starting not here, but at this line here, which is 90 degrees or p halves. And we are ending here. And here is half of a circle that is going to be 3 times pi halves, or minus p halves. So with that, we get our limits of integration. The lowest value is going to be p halves, and here 3 times pi halves. And we have it like this, okay? We can simplify a little bit the exercise. In this case, the square root of r squared, it's just r times this r is giving us a 4r squared. Dr d theta. And this is the integral that we need to solve. And now the question is, how can we solve something like that? Which method can we use? Okay, I hope you have a good idea of the way that we're going to solve it. But if not, let's find out what we're missing. Okay, the first thing that we need to do is to divide both of the terms, like if you were working with partial fractions, kind of. So if, let me write it like this, r squared is going to be divided by r squared plus 1. So we divide first term by first term, and we're getting a 1. So from here, we're getting a minus r squared, and from here, we're getting a minus 1. If we simplify, these two things can cancel, and we're getting as a residual a minus 1. So that means that we can rewrite this as 1 minus 1 divided by 1 plus r squared. So this is another way to represent what we have here inside. So let me write it like this. I'm taking out of the integral the constant, which is this 4 here, and I'm just writing 1 minus 1 divided by 1 plus r squared dr d theta. Okay? Now, in this way, it's going to be easier to solve the exercise. Let me erase what we have here. And with that, we can solve the integral. The integral of 1 with respect of the r is going to give me an r. And from here, what we're getting as a result is minus tangent to the minus 1 r d theta. So with that, we can solve, we need to evaluate from 0 to 1, and then solve the last integral. Chon, 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 chon. It seems complicated, but it's kind of easy, right? First, remember to evaluate the highest limit, which is a 1, minus tangent inverse of 1. And later we evaluate the lowest limit, which is this 0 here. So it's minus 0 minus tangent inverse of 0. And with that, we can evaluate this and get the second integral. What is the beautiful thing here? That even if this number is horrible and you don't know the value, but you have a calculator and you can get it, what we have for sure is that this is a constant. We don't have the variable theta at anywhere. So this whole constant is going to give us the constant times the variable, which is going to be theta, okay? So with that, we're getting this 4 times 1 minus tangent to the minus 1 minus tangent to the minus 0. Why am I writing this? Because I'm not sure. I don't have a calculator at this moment, so I don't have an exact value, and I don't remember which are those values, but you have a calculator and you can get it. So this is the calculus, and we're going to multiply by the theta. And with this, we need to evaluate from pi halves to 3 pi halves. And we're almost done. We evaluate the highest limit, and we subtract the evaluation of the lowest limit. And with that, we're done. You can get a numerical value, just put in all this in the calculator. Remember to use radians in order to not lose points, and everything is fine, right? So let me erase this again. And let's go to the next exercise. Okay, now what I want to do is to solve a few application problems. And actually, this exercise is extremely important because it's a way that you're going to have to solve your problem situation. Remember that in your problem situation, you have two different things to do. You have to calculate the volume inside your cookie jar, and also you need to calculate the surface area. That means the amount of material that you have in all the positions, okay? So how are you going to do that? Using double integrals. Actually, this is an application, a really common application of double integrals. You are going to have a specific formula to do that. If you want to calculate a surface area, what you are going to need is the double integral of f of x squared plus f of y squared plus 1 differential of area. This is a formula that you have to keep in mind. So basically, what you need to do is to get the partial derivatives. What we have here are the partial derivative with respect of x and the partial derivative with respect of y. How are we going to do it? Extremely easy. First, we're going to get from here an expression for z, which remember is the height, and we're getting a 6 minus 3x minus 2 times y, okay? So if we get the partial derivative with respect of x, here we're getting a minus 3, and a partial derivative with respect of y, we're getting here a minus 2. So these two are the partial derivatives that we need to substitute here in these positions. What is missing? What we need to get is the differential of area. And in this case, remember that the differential of area is actually the region that we're going to have here in the floor, this triangle that we're having here. So this is what we need to establish in which direction are we going to integrate. If moving in the X direction or doing it in the Y direction, okay? So to do that, I'm going to show you a next figure like this one. This triangle that I have here in purple is exactly the same that we have here in green. And you will say, Mariana, how did you get that formula that now you have there? Okay, remember that this region is always happening in the floor. So Z has to have a value of 0. So from this equation, if Z is equal to 0, look, we're getting a 3x plus 2y equal to 6. So we can get an expression for y. This term is going to be subtracting 6 minus 3x. And y has to be 6 minus 3x divided by 2, which is the expression that I have here. So this line is the line that we have here, okay? Important to say. If that is correct, also you can get the limits of integration, which are these cuts here, these edges here. In which direction are we going to solve the integral? It doesn't matter. You can do it first in y, or you can do it first in x. So if you're doing it first in y, you are getting in by this line, which again is y equal to 0, and you are going out by this line, which is this expression, okay? So let's build the result. S has to be the double integral of the square root of f of x squared, which in this case is this minus 3 squared, plus f of y squared, which is this minus 2 squared, plus a 1. And instead of differential of area, we need to write dy dx. This one is inside the integral. And the limits are 0, and here minus 3 halves of x plus 3. And for x, the lowest limit is this 0 here, and the highest limit is this 2 here, from 0 to 2. I already have this exercise solved here to avoid writing a lot. And as you can notice, I have exactly the same information here in the slide. If we put this into calculator, from here we're getting a 9, from here we're getting a 4 and a 1. So from there, this is the square root of 14. The square root of 14, if we integrate it with respect of y, is giving us a square root of 14 times y, which needs to be evaluated in these two limits. So we substitute this here, and then we subtract with the 0. And from there, we're getting this value. The square root of 14 was taken out of the integral, and then we integrate with respect of x. So that's why here we have an x squared divided by 2 times this 2 is giving this 4, and the square root and the integral of 3 is 3 times x. So we're getting these values evaluated in the lowest and in the highest limit, and we're getting this result. What is this value? Okay, actually that value has to be the amount of area or surface that we have here in this triangle. That is what you need to do for your problem situation. You need to calculate the volume, and also you need to calculate the surface area that you're going to have there. I have here another example. It's kind of similar. Now the only difference is that the function is x times y. And they are asking us, what is this x times y? This weird surface that we have here in red getting in like in yellow and green, this is x times y. And they are telling us that the region is bounded or determined by something that by the piece that is inside the cylinder of radius 1, which is this region here. We have to do exactly the same if we are trying to calculate the surface area always, if we want to calculate surface area, we need the double integral of the square root of f of x squared plus f of y squared plus 1 differential of area. Okay? We need the partial derivatives. F of x has to be the derivative of this with respect of x, which is a y. Z of y is going to give us an x, and these two has to be substituted here. And now, which is the way to substitute this differential of area? Which is the better way to do it? Dx dy, dy dx, r dr d theta, you have to tell me. Okay, in this case, yes, it has to be with polar coordinates. Why? Because the region that is bounding my surface is actually a circle, a piece of circle. So it's better to do it with polar coordinates. I have already here the solution. I'm substituting f of x and f of y here in the formula. And then I'm providing you the result. In this case, I'm not solving the exercise because it's kind of easy. The formulas are really friendly, so you don't have to worry about a lot of things. Just keep in mind that x squared plus y squared has to be r squared, which is what we have here. Also, that this differential of area is r dr d theta. And with that, we can establish that if this is a cylinder of radius 1, the radius is running from 0 to 1. That's why we have here. And because it's a whole turn, it's the angle running from 0 to 2 pi. And with that, we can solve the equation. This integral has to be solved using the method of correct substitution. So you have to use substitution. Our u has to be 1 plus r squared. And the u, it's going to be 2r dr. And with this substitution, you can solve the integral, and you are getting what we have here inside. Okay? This is the numerical value, and again, the meaning of that is actually the amount of material that we have in this surface here. Okay? We're going to have one more application, and we're done with this practice. I hope you are getting everything clear and you are getting a lot of good examples. And one extra application is how to calculate the mass of an object, and also we can calculate the center of mass. Also, there are so many other applications like getting the moment of inertia and things like that. But these are like the formulas that you have to keep in mind in order to calculate the mass density, the mass and the center of mass. Okay, give me a second. Awesome. Okay, so let's try to analyze a little bit the formulas. What we have here is that the mass is going to be the density times the differential of area. Why? Because remember that in particular for this exercise, we are considering what the text is saying. Mass and first moment formulas for a thin plate covering a region R in the XY plane. Let's try to explain what we have here. Remember that there are 3 types of density. We can have linear density, we can have surface density, and volumetric density. If we consider linear density, that means the total mass of an object along a length. If we think of a surface density, that means how much mass do we have in a differential of area in a specific area. And the most common one is the volumetric density, which is the mass of the object that we actually have in a volume. Oh, my mistake. Let me erase here. Here we don't have volume. What we have is volumetric density, like this. In a specific, if we're thinking of the mass that we have of a plate, of I don't know, a folder, something plain, something like this, we're thinking of something like that. We're having a relation like this, a surface density. Look from this equation. The mass is going to be this density times the area. So basically, if we don't have a regular area, a regular shape like a square, like a circle, like something like that, or the density is not constant, that means that we have a heaviest size of the plate, maybe because the material is changing, and in a certain piece you have I don't know, plastic, and then you have aluminum, and then you have like a mix of elements there, and you have a variable density. What we can say is that the mass can be calculated as the double integral of this density times the differential of area. And this is what we have in this formula, okay? This is the way to calculate the mass. What else? If we need to get the center of mass, what we first need is the first moment of inertia. And look, m of x is going to be the variable y times the density differential of area. And the moment in y is going to be the variable x times the density differential of area. And with that, we can get the coordinates of the center of mass. Don't worry, you don't need to learn all these formulas. This is just an application, as I was showing you the one for the surface area. Here are formulas to do it with the mass, to the center of mass, and things like that. But let's solve an exercise, and this is the last one that we're going to have. Okay, so let me change the slide. Cheeky, quiet. Tui. Okay. We're going to find the center of mass of this thin plate with variable density, okay? Let's consider the shape of the plate is actually something like the triangle that we have there. And look, they are telling us that a thin plate covers the triangle region bounded by the x-axis. Remember, and I will be insisting with this line here, it's y equal to 0. The x-axis is the equation y equal to 0. The line x equal to 1, which is this vertical line here. And we have y equal to 2 times x, which is this line here, okay? The plate density is variable and is changing with this relation, 6x plus 6y plus 6. They are asking us to calculate the mass, the first moments, and the center of mass about the coordinate axis. So let's start. The mass is the easiest one. Remember, this is going to be the double integral of the density, any expression that you have for the density, times the differential of area. So with that, we can rewrite this as 6x plus 6y plus 6. And we have to change this dA, this differential of area, by dx dy or dy dx. As you can see, the function is extremely easy, so it doesn't matter by which variable that we're starting. So you can decide if to do to have the integration in the y-axis or to do it in the x-axis. Okay? To change a little bit, because the previous exercise we solved it in the y-axis, we're going to do this one with the x-axis. If we move in the direction of the x-axis, we are entering to the surface here in this line, and we're going out in this one, okay? So we need an expression in terms of x. So from here, x has to be y divided by 2. And we are going out by x equal to 1. So those are the limits that we are going to use, y divided by 2 and x equal to 1, starting the integration in the x direction. And later we require dy. Remember that for the second integral, we need the lowest value of y and the highest value of y. So in this case, it's going to be a 0 and a 2. 0 and 2. And we can solve the integral now. If we get the integral with this with respect of x, this is going to give us a 6x squared divided by 2. Here, we're going to get a cy times x, and this is 6x. And we need to evaluate from y halves to 1. We're getting a 3x squared. Now, I'm going to write it here. These two are going to be simplified by a 3. And we're going to have an evaluation of the upper limit, which is this thing here. And we need to subtract the evaluation of the lowest limit, which is this y divided by 2. So this is going to be y divided by 2 squared plus a 6y times y halves plus a y half. Okay? Let's try to simplify a little bit this because it seems kind of long. From here, we're getting a 3. And from here, we're getting a 6, which is actually a 9. Here, we're getting a 6 times y. And from here, we're getting a y squared divided by 4. From here, we're getting a 6 divided by 2, which is a 3 y squared. And from here, we're getting a y half. We can simplify a little bit more. Because here we have 6, and here we have 6y and y half. So this is going to give us 16 halves is 12 halves, plus 1 half is 13 halves. And if we sum 1/4 of y squared plus 3 y squared, we can change these 3 into fourths. So we have 12 fourths. Plus this one, we're getting a 13/4 of y squared. And now we can get the integral, okay? So if we do that, we're getting a 2y plus a 13 halves of y squared divided by 2. And from here, we're getting a 13/4 of y cubic divided by 3. And we need to evaluate from 0 to 2. Please do the substitution in order to get the result and tell me which is the numerical value that we're going to have here. That is going to be the mass of the plate. Okay, people? Or not? Again, a mistake. I forgot the parentheses here. So we have a mistake here. Let's change this here. Delete and delete. And let's rewrite it this. This is a 3. From here, we're getting 6y plus a 6. From here, we're getting a minus y squared divided by 4. From here, we're getting a minus 3y squared. And from here, we're getting a minus y halves. So this has to be simplified. So this is giving me a 9. 3 plus 6 is giving me a 9. And from here, 6 in halves is 12 halves. Minus 1 is 11 halves of y. And these two are going to give us 3 in fourths. It's going to be minus 12 fourths. Minus 1 is minus 13 fourths of y squared. So you need to solve this integral to get the final result. Okay? Let me fix it here. You have to be careful to not make mistakes like this one. So we're getting 9y plus 11 halves of y squared divided by 2. And from here, a minus 13y cubic divided by 3 and the 4. And we need to evaluate from 0 to 2. And this has to give us a result of, okay, correct, 14. And with that, we're done with the mass of the plate, okay? So let's do the substitution. So if we start by the upper limit, from here we're getting a 3 times 1 squared. If we substitute the 1 here, we're getting a 6 times y. And from here, a 6, if we substitute here. And now we are going to evaluate the lower limit, which is actually a 3 times y half squared plus a 6y times y halves plus a 6 times y halves. And with that, we can get the result. So if we simplify a little bit this, we're getting a 3 plus a 6y plus 6. From here, we're getting a minus 3/4 of y squared. From here, we're getting a minus 3y squared. And from here, we're getting a minus 3 times y. And this is what we need to simplify. This is giving us a 9 of these 3 and 6. Also, from here, we're getting a 3 times y. This 6y minus 3y is giving us this 3y. And later, what we need to do is to add these things here. So it gives us minus 15/4 of y squared with respect of y. And we integrate this and we evaluate with both of the limits. And with that, we're getting our final result for the mass. Which in this case is going to be a number, thank you very much, a number 14. Perfect. So I'm going to stop the video now. What you are going to do with my next question is to provide the coordinates of the center of mass. How are you going to do it? Remember, you need to follow the formula. Let me write it with another color. Let me write it here. We got a mass of 14. And you need to establish a way to calculate m of x. So if we go to the formulas that we have in the previous slide, m of x is going to be given by the double integral of y times the density, which is this formula here, and times the differential of area. In this case, the differential of area, it's going to be, again, dx dy or dy dx. Maybe if you think that it was kind of more difficult to do it with dx because we get the half there and it's making a lot of noise, it's correct. We can do it first in the y direction, like doing it here, like this. And in that case, the limits of integration will be y0 and going out here with this 2x. So the limits are going to be 0 and 2x. And the smallest limit of x is this 0, and the highest limit of x is this 1 here. So we get a 0, 1. Okay? So you need to solve this formula. And once you have it, you can calculate with that the y component of the center of mass. The y component of the center of mass is m of x divided by the mass. So if everything went right, you solve this integral and you are getting as a result that this formula is going to give us an 11. So the y coordinate of the center of mass has to be 11/14. Now you need to get m of y. Let me build the formula. In that case, it has to be an x times the density. Let's keep the same limits of integration. A 0 and a 2x, and here a 0 and a 1. If you solve this integral, beautiful people of this class, what you are getting as a result is a number 10, correct. So the x component has to be m of y divided by the total mass, so we're getting a 10/14. Okay? So the center of mass, it's going to be this x component and y component. And then you have a way to apply double integrals. Congratulations, we're done with these exercises. Thank you very much for being here, and I hope you enjoyed the video. See you, students. And let me pause this, stop the recording.